Good afternoon, everyone. Welcome to our Monday afternoon Sky Talk here at the 55th Design Automation Conference. My name is Mackenzie Ross. I am the current chair of the Worldwide Women in Electronic Design, and it's my great pleasure to introduce to you our speaker, Anna-Katrina Shedletsky, who's going to be telling you all about automating intelligence, machine learning, and the future of manufacturing. Enjoy.
Thank you very much. Hello, thank you for coming, and I hope you'll learn something from this talk. I've specifically tried to format it from the perspective of more of learning and takeaways than anything else. So hopefully there's some useful stuff in here, and we'll get right started. So my name is Anna Shedletsky. I'm a mechanical engineer by training. I was at Apple for 6 years, designing mechanical components for iPods and led system product design for Apple Watch Series 1. I then left to start a company called Instrumental, where we're building essentially data software for manufacturing that has artificial intelligence built in. So let's talk about the kind of the status quo in the world today. So automation is old news. Everybody here knows that. A lot of the industries represented here have been automated for years. They don't work if they're not automated. But there's other parts of the kind of the world that are still quite manual. And then there's some industries that are kind of in the middle, where they have some automation and some not. And it's actually these industries that are kind of in the middle that are creating all of the I would call it media craze around like, okay, automation is stealing jobs. For many of these things on this side, it's been automated for a very long time. And so the way that I kind of look at it is that automation, the battle for automation was won by the steam engine with John Henry, and since then we're just trying to catch up to what was already proven to us. And there's kind of some key factors: miniaturization, needing clean processes, such as for semiconductor, and then in actuality, just not having enough people to do the jobs for the demand created by the product. So the result of automation is actually what we're going to be talking about, which is that there will be an opportunity for a massive amount of data to be readily available that wasn't available before. And some industries have access to this, and others that are still now just automating will be getting access to this for the first time. And that creates an opportunity to actually use this data in smart ways to improve processes to get better manufacturing outcomes, which is probably what you all are here today at DAC to learn about, is how to get better manufacturing outcomes. So to start, as promised in my talk, I want to talk about some buzzwords. This will be the only place in the talk where there's any buzzwords. So we'll get it all out of our systems. I hate buzzwords. I don't think they're particularly helpful. But I want to kind of explain the grounding so we all have kind of the right grounding for this talk. So Industry 4.0, big buzzword. The 4 refers to different stages in industry, literally starting with steam power. That was the first stage. Electricity automation is kind of like where we are right now, and then this opportunity for network. And the network piece is where you'll hear this word industrial IoT. I would say that most industries are like here, like 2.0. And so what's really challenging about Industry 4.0, and this is kind of heretical, but I will say it, is it actually damaging companies that are trying to build this, because you need to do these first steps first, and these things aren't glamorous. They're things like getting good data sets that are clean. It's not like fancy whiz-bang AI systems that are going to magically improve your process. And so because there's so much advertising around the whiz-bang stuff over here, it makes it really difficult to actually build businesses that can move industries from the 2.0 to the 4.0. So I actually really hate this because I think it does a disservice to the industry, but that's kind of the context for that piece. Then there's this other word, artificial intelligence. And so this is essentially, the way I look at artificial intelligence is it's a toolbox. And inside the toolbox, you have different kinds of tools. You've got a screwdriver, you've got a spanner wrench, you've got a monkey wrench. They're for different things. And so there's different elements of artificial intelligence, ranging from some buzzwords like machine learning and deep learning. So these are systems that learn from large data sets, either supervised or unsupervised, and create insights that feel magical. So that's why they're so buzzwordy. There's some traditional stuff that's been around for 10, 20 years, well utilized in the semiconductor industry and other industries around computer vision and machine vision. These mean the same thing. They're just different ways for people to say them. And then the last one is there's a tool in the toolbox that is math. And there's nothing fancy about it. It's just math. It's Pearson coefficients, it's statistics. They use this word called big data, but it's just math. And so that's actually one of the most powerful tools in the toolbox, but it gets like the least street cred because it doesn't have a fancy name. But that's kind of the mapping of the buzzwords, and that will be the last buzzwords that we talk about, because essentially I was kind of alluding to IoT projects like fail, 75% of them according to a Cisco survey. You can look up this online. This is a screenshot directly from the article available. So IoT projects that are pushing towards that Industry 4.0, 25% of them are successful and the rest fail, and it's because they're about the whiz-bang and they're not about the basics. And the basics are really about improving better outcomes. That's what we care about, manufacturing outcomes. Those are really unsexy things like yield, throughput, uptime, efficiency, time to market. And if you're not affecting one of these parameters, like get out, right? Like it's not worth it. So unfortunately, the reason why the whiz-bang stuff gets a lot of press and interest and intrigue is because it sounds really easy. Like you're going to give a whole bunch of data that's kind of in a garbage state, and magically someone's going to tell you how to improve your process. But it doesn't work like that. Better outcomes require hard work. It means finding problems and solving them. And so today, this process is very manual. It involves a lot of people. First you got to find your issues. You got engineers to help you do that. You got to root cause those problems. That takes a long time. You got to figure out what to do about it in your corrective action, and then you actually got to validate the solution and put it in place. And this is manual, inefficient, and actually quite porous because you're relying on humans to find the issues. And so there's opportunities here to actually try to automate this process. And this is kind of where there's like this is slightly heretical because it's talking about a process and automating a process as opposed to like, let's just put AI on the line and make things great. No, what we're really trying to do is actually get through this process faster so that you can get to market faster and have higher quality. That's better outcomes. And so from that piece, how do we accelerate that? And the core secret is really unsexy. It's just data. It's better data. It's high resolution. It's not the pass-fail stuff that's going into your MES system that nobody looks at because it's so low resolution it's not valuable from an engineering perspective. It's literal details about the process, everything you can get about it in a clean format that's actually able to be processed. And today, engineers do this. They collect this data from different sources. They put them into spreadsheets. They do some basic statistics, and they get results. And so that process is what can be automated, but it relies on clean data. And so here's kind of the flow chart of how you go from data to success. You take the data, you combine it with some math and statistics. You have two data sets. You can look for correlation between those data sets. You find correlation, you have an insight. Once you have an insight that there's correlation, antenna performance is related to position, the geometric position of the antenna, then you can actually get an action. Like, well, let's move the antenna to optimize performance. And then once you have the action, you can actually get better outcomes, which is hopefully better performing antennas. So this field about automating this feedback loop, Industry 4.0, that stuff is very nascent. And as I said, there's a lot of buzzwords, so it's really hard to kind of sift through the marketing speak and get to what really matters. And so I've been asked today to actually describe a case study in extreme detail, which I'm going to do, of how you can actually, with better data, you can create a better outcome, and walk through that and kind of the opportunities for that going forward. So I mentioned the better data piece. The reason it's not readily available is because it's hard. A lot of the data isn't really accessible. If it does exist, it's trapped on machines. There's no place for it to go. It's in an MES system that nobody has access to, or is only storing like some portion of the data, but not the highest resolution version. Sometimes, depending on where you're building, the factory internet can be really slow. So being able to get access to that data anywhere outside the factory is tricky. I think also the industrial complex is really concerned about the cloud and whether it's secure. The cloud is super secure. You all do your banking online. Like, it's secure enough for that. It's secure enough for your data. And then there's more data than you can look at. So there's just so much volume of data that you can't have an engineer actually trying to run this thing in Excel. There's too many rows in the spreadsheet. The whole thing will crash. And so you need new systems for that. And so my company has solved these problems in a couple of ways. We've created a vertically integrated cloud infrastructure, so it goes all the way from the factory floor up to wherever your laptop is that you're communicating with the data wherever you are. You could be on a beach, you can be in your office, you could be on the line. We've designed it for imperfect connectivity. Our main use case is in China today, which is one of the most hostile networking environments on the planet, and it works there. So it works almost everywhere as a result. And then because there's so much data, it means you need algorithms. So what's different about using data in an intelligent way is not just to hoard it and have this big filing cabinet of data. It's to actually have algorithms that can run over it for you because there's too much of it for you to pull into an Excel spreadsheet and look for the results yourself. So as I mentioned, we're a vertically integrated stack from capturing images. So we are the thesis we had is we need high resolution data. Most of the manufacturing partners we work with don't actually have great high resolution data. So we created a data type that's really valuable that they can use to get that data. And we've decided that was an image. So an image is a great measurement type because you don't need to know what you're looking for when you take the image, but you can go back to it and see a lot of stuff. Position information, what's there, what's not. There's a lot of useful stuff in an image. So we actually help our partners to actually capture these images on our equipment or theirs if they have it. We find and track these issues. We have software that enables engineers to find and track issues in a software interface, not physically on the line. And then we have machine learning algorithms that enable our customers to actually intercept anomalies in real time on the line. And so this kind of feedback loop all the way around that circle, we're supporting that entire circle. And that's what's useful about a product like this. There are certainly products that cover this piece where you can do image inspection on the line. Keyence, Cognex, Radiant, a whole bunch of companies that do this. There are certainly companies that can build databases for you that you can pull data out of. And there's certainly all sorts of companies telling you that they have AI solutions that will help you find useful insights. I think the benefit in this, what's required in an industrial framework is you have to provide all those things in order to create a full value loop. Otherwise, you have customers patchworking 5 different things together. So let's talk about the case study, which is what I was invited here by Mackenzie to walk through. So we work with a lot of Fortune 500 companies that don't let us talk about their data or never let us show it in public. So the data that I am showing in public, I have permission to show, but it's from a smaller company. So just imagine this for other types of applications as well. So Pearl Auto is a company that built a backup camera that's in a license plate form factor. And so it has some cameras, and it actually has a solar module down here, which is going to be important. That's a kind of a key part of the problems that they have with this product. And so they started with us using instrumental in development, which is another kind of unique piece. Like development is a place that I think a lot of industrial companies kind of view as like, oh, that's just a waste of money. Like as fast as we can get out of development, the better. But actually, you have massive opportunities to save a ton of money by accelerating development and doing a better job on it, and increasing the quality in development before you even get to production. Because in development, the design is still flexible, you can make changes. But then also in production, like how they use the system to prevent a line down that saved them $500,000 in one day. So specific process flow of how this works. So this is a consumer electronic product. We're at the factory that is building the product, assembling it, and they have 2 lines. They have a sub-assembly line for the solar module, and then they have a final assembly line for the rest of the product. So they put an instrumental station at the end of the finished module so that they could capture an image of what the module looked like after gluing. They have to glue, essentially they have a raw solar module that looks like this. They put down some liquid optically clear adhesive, and then they got to put that part on it, and there has to be no bubbles. It's actually really hard if you do any kind of lamination, TFT, I don't know if there's any display people in the audience, that stuff's hard. And so they had one main station here. They found they had problems, so they actually added one halfway through development upstream for the pre-glue. Final assembly line has lots of steps. And they put 2 stations at the end, a pre-snap station where they're able to see inside the product with some of the details of the inside before it's closed up, as well as some finished goods stations that let them look at the reveals between plastic and metal parts. They want Apple level quality, and that's how you get Apple level quality, is you actually have to look for it. So they did 2 other things with their process that is unique. One is when they're building units. So this is a small company. They don't own their own factory, and they don't have people at the factory all the time. And so when the factory is building and nobody's there, when there's problems, it's hard for them to actually understand what's going on. So if something were to fail at this point in the line, they actually had a process where it would get accelerated. They'd skip all these steps. They'd go to this pre-snap station, and this station take images before they send it to repair. So the engineers here can wake up in their morning, see what happened and failed, and actually have some information about what to work on. They can actually see the failures in action, and then if those units go back to the line, they have a before and after picture. The other thing they did is at the end of in a development process, at the end of the line, this data is going to reliability lifecycle strife testing to make sure that the design is good, that validation step. And they actually were putting units back through the stations after reliability, so they had before-after pictures. That's an important process change that they made that saved their butts later. OK, so here's how it works quickly. You take an image on the line. And the system can look various different ways. It doesn't always have to look like this. And we can use our customer systems as well to take images. They put the part in. They take an image. It gets uploaded to the web, to a database. They're able to actually see that data in a GUI, in a UI interface that's designed for engineers to use. It's easy to use. You can learn how to use it in 10 minutes. You can use that software to actually deploy machine learning algorithms onto the line without knowing anything about machine learning. You just identify defects of things that you found or things that you know are good, but if you see anything different than this algorithm, please tell me. And so you can actually set these up, and then these can go to the line. And so now when new units come through, if they fail those tests, it will actually fail on the line. And so this creates a really easy way to put a test either on the line live or to just monitor it in the cloud before you make it live. Make sure that it's not going to cause chaos on your line with a high false failure or false pass rate. So I'm going to quickly go through some of the types of things they found in development. And specifically, one of the very obvious ones that's easy to show, and I'll actually show a video of the algorithms working, is this case where they found some units that had missing screws. So this is development, missing parts, super common. And so they're actually able to use the software to find these. And so if I can get a go on the video. OK, cool. So I recorded this yesterday on this data set. So this is in their development time frame. And you're able to zoom in. It's a full 24 megapixel image. And here, I don't know, as an engineer, I don't know that there's any problem with this region, but there's not a lot to look at. I'm going to look at this region and see what's interesting. So I'm actually defining a region of any size, of whatever I want in it. I clicked a button to look for anomalies. What's happening right now is that 400 GPUs are spinning up in the cloud, running in parallel, processing that crop, and is now sorting them in order from most anomalous to least anomalous. And you see that it's found 2 that have missing screws. And so that's interesting as an engineer. Like, oh, we got missing screws. I didn't know that before. And so I clicked another button here, more like this. Now it's detecting similarities. It's going to resort these based on most similar to that unit. And now we can see that there's 3 of them. So that's a problem. I don't ever want to make units with missing screws. That one's obvious. And so here I'm actually setting up a test to be able to find those missing screws. I'm giving it a name. I'm going to click Save. And that test is set up and now can be live on the line. That's how easy it was to deploy machine learning algorithms to the line. And you can use this so we can stop it because now it's just looping. Yeah. You can use this for things like anomalies where you don't know what you're looking for. That's kind of the key problem with today's computer vision technology is you have to have defect units, limit samples, specs. But in development, you don't have any of those things. You can barely even build one unit, never less a golden unit. OK, so what are some of the defects that they found in development? These might be hard to see on the screen, but there's essentially some very small, I don't know if that's showing up. There's some very small bubbles here. So bubbles grow over time when you put them in heat soak or heat. And this is going to go on the back of a car, so it's going to get hot. And they're very concerned that if these bubbles grow too big, not only does it look ugly and cheap, that it'll actually affect the performance of the solar panel. So they needed to make sure there was no bubbles. And the way they did this is they actually put some extra station on the line, which I mentioned. And they're taking before and after pictures, before and after rel, to make sure the bubbles don't grow if there are bubbles, so that they can dial in their gluing process. Glue is a pain. And I think the next process is also a glue process. If you have glue processes in your product, you should come talk to us because they're really difficult to control and they change over time with temperature, with glue mix. If you have bubbles in the glue, it can be a problem. And so here, this is for a sealed area that needs to be IPX8 or something like that. And they're validating this performance in an air seal tester, but they need to make sure that they have a process that works that their glue machine is calibrated every day. So they use these images to understand what calibration procedure is going to work for them in a long term. Wire routing, that's one that's really difficult to do with traditional computer vision systems. Machine learning systems do really well because it looks very different than what it's supposed to look like. Here the wire's been kind of like shoved in here. It's not supposed to be there. And so this actually potentially would cause a reliability issue to this camera module. Keep in mind this photo is like this is a 4x4 millimeter thing in a photo, so it's a tiny little thing. Can also work for big stuff. But this enabled them to identify that there is a reliability risk with these units, and they can pull the specific units that had this issue and rework them so they never actually went to customers or to reliability testing. Incorrect seal placement. This is another one where there's a lot of different ways this seal could be improperly placed. It's supposed to be like nice and even. It's hard to see, but it's kind of smushed over in both of these. This is something where it could be difficult to do failure analysis on later. Having a photo is really helpful. And now we get to production. So how do they save $500,000 in a day? Well, they had a problem. First, the factory notified them of an issue in their ongoing reliability testing. So they're building units for customers. This is normal best practices to take some of those units and do some testing on them to make sure your process hasn't changed in any way that would affect the quality of the product you make. The engineer had a before and after test photos of these units and was actually able to see that there was a major problem. So the factory notified him of the problem, but he was able to log in and actually see that problem for himself, like, yes, we cannot ship that. Unfortunately, the factory had overbuilt and had actually risk-built some piece of inventory with the defective, potentially defective, the concerning module, some of which had this failure mode. Some of them did not have the failure mode. And so he actually was able to go into the system, look at the before pictures that had catastrophic failures and the before pictures that did not fail, and come up with a spec. He was able to pull together his executive team and get approval on the spec. And when the factory woke up at 4 p.m. California time, fully expecting to be down because they had this major issue, they had a spec. They had a list of the disposition. These units you've already built, you can ship. These ones need to be repaired, and you can now proceed with input. And so he was able to communicate that to the factory partner through the system, and the factory line could start immediately. So they suffered no line downtime for this incident, which normally would have taken them, they claim, at least 5 days. They would have had to fly someone to figure out what was going on and then make a disposition and come back before the line could get back up. Here's a quick case study of a secondary customer that we are allowed to share. FLIR is a leader in thermal camera technology. They built, this is the FLIR 1. Which we were fortunate enough to participate in. They had a bunch of photos taken throughout the line, similar to Pearl. Here's an example of a dark yield issue that we were able to find. And so here they have a screw that holds down this plate that holds this connector assembly, very important to the reliability of the connector. And you can see the top photo is green. That one is fine. That's what it's supposed to look like. But the second photo, you can see that the head is a little tilted, and you can see more of that silver bracket, so it's not fully seated. So these are production units that they were able to identify before these units left the factory. At the time, we didn't have the real-time system. Now we have the real-time system, so we could actually identify them at this place on the line when this is super easy to fix because it's visible. So yeah, kind of another example. So just to kind of dig into that term I threw out there, dark yield. So FLIR identified this key issue in production that functional tests wouldn't have found. And Pearl was able to figure out which units were going to fail that catastrophic test without actually running it. And what we're talking about is actually preventing dark yield. So dark yield are items that normally are yielded, units that are yielded, so they're yield, but they come back at you, either in warranty returns or unhappy customers. These are items that fail in the field that should have been catchable because you had no way to test them. And so being able to find images are actually a great way to find dark yield related items because you can usually see them even if there's no functional failure at a test. Okay, so back to what we care about, manufacturing outcomes, right? That's what we care about. And so taking this process, we've been able to completely do this part for our customer with a little bit of engagement, and we've been able to significantly support both the root cause and the validation part of any new solution. And the opportunity now would be to be able to do this corrective action piece. That's the really cool part where you could actually say, oh, like I have an understanding about what you could change about your process to improve it. And the way we do that is with data, of course, right? That's all I talk about, data. So different data types besides images. Low resolution data is only useful if you want to track things like yield. You need high resolution parameterized data And that's where you can pull it from these different places, and that's where you can use to actually create correlations. And so that's kind of the opportunity left in the space and something that we're starting to work on today already. So this is kind of my parting wisdom, I guess. So don't get caught up in the glitz and glam of Industry 4.0 because nobody's there yet. There is no company that can sell you something that really delivers on the marketing promise. And it's a shame because we all want that future to exist. So we gotta keep working towards it. Invest in, if you're gonna do anything today, if you want that future, invest in collecting and aggregating clean, high-resolution data sets. What's high resolution makes a lot of sense when you're talking about images, but what do I mean from a numbers perspective? High resolution means that an engineer can look at the data and have an understanding of several next steps that they can take to solve the problem. If they're only looking at pass-fail data, the only next steps they can get is get my hand on the units. But if they have actual performance data, full parameterized data, they can have other ideas of next steps of okay, it's not this, it's probably this, I'm going to focus on that. So that's what I mean by high-resolution data sets. So invest in collecting those and putting those in a place that are accessible to the engineers who are actually going to do this work, and then use those data sets to make the changes today so you can build better today, so you don't have to wait for Industry 4.0 to catch up to all the hype. That's all for my talk today. So thank you very much for coming. I hope you learned something that you can take away. Oh, perfect timing. Great. Okay.